July 17th, 1944. The sun hung high and white-hot over the sprawling, dusty airstrip at Saint-Pierre-du-Mont, a few miles inland from the Normandy coast. The air was thick, almost solid, compounded by the humidity rising from the French countryside and the suffocating dust kicked up by thousands of boots and rolling tires. It smelled of crushed clover, high-octane aviation fuel, and the distinctive metallic tang of hot engines cooling in the breeze. On the pierced steel planking that served as a runway, the heat shimmered in waving lines, distorting the horizon where the darker green of the bocage, the infamous hedgerows, began. Here, amidst the roar of ground operations and the distant thumping bass line of artillery fire to the south, a machine of singular brutality sat silent. It was a Republic P-47 Thunderbolt, known universally to its pilots and crews as the Jug. Standing beside it, a human figure appeared almost comically small. The aircraft was a monolith of aluminum and steel, a 7-ton flying milk bottle that dwarfed the sleek Spitfires and Mustangs operating in the same theatre. Its fuselage was barrel-chested, designed not for the graceful, balletic dogfights of the Battle of Britain, but for the brutal, kinetic physics of ground attack. But on this particular afternoon, the massive fighter bomber represented a problem. It was a weapon of immense potential energy that was failing to discharge its power effectively against the one target that mattered most. Master Sergeant Thomas "Red" Harrison, though his name could have been any of 1,000 crew chiefs across the 9th Air Force, wiped grease from his knuckles with a rag that had long since ceased to be clean. He stared up at the underside of the Thunderbolt's massive elliptical wing. The metal was hot enough to sear skin. Harrison was tired. It was a bone-deep fatigue born of 18-hour days, sleeping under canvas and eating dust with every meal. But more than the exhaustion, he felt the gnawing frustration that permeated the entire squadron. The pilots were returning with their faces grey and their hands shaking, not just from the adrenaline of combat, but from the impotence of it. They were flying the most powerful single-engine fighter in the Allied inventory, yet they were struggling to stop the German armour moving through the hedgerows. The issue was not the plane's engine, nor its pilot's courage. The issue was geometry and physics. The Thunderbolt was designed to carry bombs or limited rocket tubes on factory-specified hardpoints. But the German tanks, the Panthers and the terrifying Tigers were elusive targets. Dropping a 500-pound bomb on a moving tank from 3,000 feet was an exercise in probability that favored the tank. The pilots needed more precision. They needed volume. They needed to saturate the target area with high-velocity explosives, but the rulebook, written by engineers in comfortable offices in Farmingdale, Long Island, said there was no room left on the wing. Harrison looked at the pile of materials scrounged from around the airfield. There were lengths of steel pipe, discarded packing crates, and coils of heavy-gauge baling wire liberated from a nearby French farm. Beside them sat rolls of silver industrial adhesive duct tape. It was a tableau of agricultural simplicity sitting in the shadow of high-technology warfare. What was about to happen on this hard stand would not appear in any technical order or maintenance manual. It was a violation of military protocol, a hazard to aerodynamics, and arguably a court-martial offense. But the sergeants of the flight line operated under a different jurisdiction. The law of survival. In the next hour, using materials that belonged in a barn rather than an airfield, they would fundamentally alter the lethality of the P-47 Thunderbolt, transforming it from a heavy escort into the most feared tank-killing predator of the Second World War. To understand the gravity of this moment, a mechanic holding a pair of pliers and a roll of wire, we must step back from the heat of the French summer and examine the precipice upon which the Allied invasion balanced. By mid-July 1944, the euphoria of D-Day had evaporated, replaced by the grinding, bloody reality of the Battle of the Hedgerows. The Allies had secured the beaches, but they had not broken out. They were trapped in the bocage, a checkerboard of small fields separated by ancient earthen embankments, topped with thick, impenetrable tangles of roots and trees. These hedgerows were natural fortresses, impervious to rifle fire and capable of swallowing entire tanks. The German Wehrmacht, masters of defensive warfare, had turned this terrain into a slaughterhouse. Their panzer divisions, equipped with superior armor, lay in wait. A single Tiger tank, hidden in the shadows of a sunken lane, could hold up an entire American battalion. The Allied advance was measured in yards and paid for in blood. General Omar Bradley and the Allied High Command knew that to break the stalemate, they needed to unleash their overwhelming air superiority. But air power, traditionally defined by strategic bombing of factories or dogfighting at 20,000 feet, was struggling to translate its dominance to the mud and leaves of the tactical battlefield. The disconnect lay in the evolution of the air war itself. For years, the primary doctrine of the United States Army Air Forces had been high-altitude precision daylight bombing. The stars of this show were the B-17 Flying Fortresses and the B-24 Liberators. Fighters were considered little friends, escorts whose sole purpose was to keep the Luftwaffe off the bombers' backs. Ground attack, the dirty, dangerous business of flying at treetop level to strafe trucks and tanks, was a secondary consideration, often viewed as a misuse of expensive airframes and highly trained pilots. Consequently, the development of specialized ground attack munitions and mounting systems had lagged behind the rapid advancements in engine performance and airframe design. Into this doctrinal void fell the P-47 Thunderbolt. Designed by Alexander Kartveli at Republic Aviation, the P-47 was a monster. It was built around the Pratt & Whitney R2800 double Wasp engine, a piece of engineering so massive it dictated the entire shape of the fuselage. The plane was heavy, fast, and incredibly durable, able to absorb punishment that would disintegrate a Mustang. But as the air war over Europe shifted in early 1944, with the Luftwaffe's fighter force decimated, the P-47 seconds were increasingly tasked with going down on the deck. The pilots found that while their 850 caliber machine guns could shred trucks, trains, and infantry, the bullets simply bounced off the thick hide of a Panther tank like hail off a tin roof. The introduction of the unguided rocket was supposed to solve this. The British had seen success with the Hawker Typhoon firing RP-3 rockets, and the Americans were rushing to field their own version, the M8 high-velocity aircraft rocket. The M8 was a 4.5-inch fin-stabilized projectile carrying a high-explosive warhead. It struck with the force of a destroyer's shell. But the delivery system was the bottleneck. The standard American launch mechanism was the M10 rocket launcher, a cluster of 3 tubes made of a peculiar plastic-impregnated paper, or sometimes magnesium alloy, designed to be jettisoned after firing. These launchers were drag-heavy, cumbersome, and scarce. More importantly, a P-47 was typically limited to carrying just one cluster under each wing, giving a total of 6 shots. Pilots found that in the chaotic, terrifying seconds of a strafing run, 6 rockets were often not enough to guarantee a kill against a dug-in tank. They needed more shots, or they needed a way to carry rockets without the massive drag penalty of the cumbersome tube clusters. This is where the high-level strategy meetings in London and Washington collided with the pragmatic reality of the flight line. The engineers calculated drag coefficients and wing loading limits. The mechanics calculated how to keep their pilots alive. The disconnect was physical and philosophical. An engineer sees an aircraft as a finely tuned system of balances. A mechanic sees it as a truck that needs to carry more freight. In the dusty dispersal areas of the 9th Air Force, specifically within units like the 366th Fighter Group, the ground crews began to look at the P-47 not as a sacred piece of technology, but as a chassis waiting to be modified. The technical challenge of the Thunderbolt was its laminar flow wing and the complex plumbing of its internal systems. The R2800 engine required a massive network of ducting to feed the turbocharger located in the tail, meaning the belly of the aircraft was packed with sensitive equipment. You couldn't just drill holes wherever you pleased. Furthermore, the wings housed the 4 heavy machine guns per side, along with their ammunition belts, fuel lines, and hydraulic systems. Adding weight to the wings changed the center of gravity, altered the stall speed, and affected the roll rate. The P-47 was already a heavy aircraft, often taking off at weights exceeding 7 tons. Overloading it was a recipe for a takeoff crash, a tragedy that was all too common on the short, temporary airstrips of Normandy. However, the specific innovation that would become legend did not require drilling into the wing spars or rewriting the aerodynamics manual, at least, not officially. The mechanics realized that the existing hardpoints, the heavy steel shackles designed to hold 500-pound bombs or enormous drop tanks, had a structural integrity that far exceeded their typical load. The serendipitous breakthrough came with the realization that the M10 rocket tubes, while standard, were not the only way to launch a rocket. The rockets themselves were self-propelling. They didn't need a gun barrel, they just needed a rail to aim them and an electrical impulse to ignite the motor. The narrative of the duct tape and baling wire modification is often simplified, but the technical reality is a testament to high-stakes improvisation. The ground crews, led by figures whose names have largely faded into unit histories, began scavenging. They took the steel launch tubes, sometimes the M10S, sometimes modified infantry bazooka tubes, and later the zero-rail mounts, and looked for places to attach them. The standard configuration allowed for a triad of tubes. The mechanics wanted more. They began stacking the tubes, binding them together not with factory-machined brackets, which were stuck in supply depots in England, but with heavy-gauge wire twisted tight with pliers. But the true stroke of genius, the move that bridged the gap between absurdity and lethality, was the integration of the firing circuits. A rocket needs an electrical charge to fire. The P-47's stick grip had a button for bombs and a trigger for guns. It did not have a selector switch for an unauthorized battery of 8 or 10 rockets. The mechanics had to jury-rig the electrical system, splicing into the bomb-release solenoids or the gun camera circuitry. They ran wires along the exterior of the landing gear struts, taping them down with industrial adhesive tape, the duct tape of the legend, to prevent them from flapping in the 300-mile-per-hour slipstream. Consider the sheer audacity of this engineering. A modern aircraft is a sealed system. To tape wires to the outside of a hydraulic strut, exposed to the freezing air at altitude and the searing dust of the runway, was to invite failure. Yet, these connections held. The baling wire was used to brace the swaying clusters of tubes against the sway braces of the bomb shackles, ensuring that when the pilot pulled the nose up, the rockets remained aligned with the gun sight. It was crude. It looked, in the words of one pilot, like a junkyard explosion under the wing. But it meant that instead of carrying 2 bombs or 6 rockets, a single P-47 could now loft 8, sometimes 10 rockets, effectively becoming a flying destroyer. This technical transgression required a deep understanding of the aircraft's tolerances. The Pratt & Whitney R280059 engine generated 2,000 horsepower, driving a massive 4-bladed Hamilton Standard propeller. This power plant provided the brute force necessary to lift the unauthorized weight. The mechanics knew the engine's curves. They knew that if they pumped up the manifold pressure and used the water injection system, a method of spraying water into the cylinders to cool the fuel-air mixture and increase density, they could squeeze out nearly 2,300 horsepower for the critical takeoff run. They were betting the lives of their pilots on the engine's ability to overcome the massive drag induced by the jury-rigged tubes. The drag was significant. Every square inch of surface area facing the wind creates resistance. By strapping bundles of tubes and taping wires to the struts, the mechanics were ruining the carefully calculated aerodynamics of the Thunderbolt. The top speed would drop, the range would decrease, but the trade-off was firepower. The Superbolt, as some jokingly called the overloaded beasts, sacrificed grace for a sledgehammer blow. The operational impact of this improvisation was immediate and terrifying. The first pilots to test the configuration taxied out with trepidation. The aircraft felt heavy, sluggish. The control stick, usually responsive, felt like it was set in concrete during the taxi. As they lined up on the pierced steel planking, the throttle was advanced to the stop. The R2800 seconds roared, a sound that vibrated in the chest cavities of the ground crews watching from the grass. The planes lumbered forward, eating up runway, refusing to lift until the very last moment. When they finally clawed their way into the air, they were slow. But they were airborne. The proving ground was the chaotic landscape south of Saint-Lô. It was here, in late July, that the German Panzer Lehr Division was massing for a counterattack. The German tankers were accustomed to air attack, but they had learned that fighter bombers were inaccurate. If they stayed in the shadows or kept moving, they could survive. They were unprepared for the volume of fire that was about to rain down upon them. When the modified P-47 seconds arrived over the target area, the pilots didn't have to rely on a single lucky bomb drop. They could ripple-fire rockets in pairs or salvos. The sensation for the pilot was visceral. Pressing the firing button unleashed a sequence of whooshing roars that could be heard even over the engine. Smoke trails erupted from under the wings, momentarily blinding the pilot, as the aircraft shuddered from the recoil and the sudden shift in weight. Down below, the effect was apocalyptic. The M8 rocket warhead was capable of penetrating the top armor of a Tiger tank or blowing the tracks off a Panther. But even near misses were devastating. The concussive force of 8 rockets exploding in close proximity to a tank column shattered treads, cracked optics, and turned the internal compartments of the tanks into resonance chambers that liquefied organs. But the psychological impact was even greater. A tank crew inside a steel box feels invincible against bullets, but helpless against high explosives arriving from the sky. The sheer volume of rockets meant that there was no safe place. The Jabos, the German slang for jag bomber or hunter bombers, were suddenly everywhere, and they weren't missing. The statistics from late July 1944, specifically around the time of Operation Cobra, the American breakout, tell the story of this transformation. In a single day, pilots from the 9th Air Force, flying these overloaded wire-trussed Thunderbolts, claimed the destruction of dozens of armored vehicles. The number 86 tanks is often cited in unit histories for the weeks following the innovation. While the exact verification of tank kills from the air is notoriously difficult, fog of war often leads to double counting, and a damaged tank can sometimes be repaired. The disruption was undeniable. German columns ceased to move in daylight. The strategic mobility of the Wehrmacht, the very foundation of the Blitzkrieg, was paralyzed by a mechanic's trick. There is a specific account from a lieutenant in the 366th Fighter Group that captures the human dimension of this technical shift. He recalled diving on a column of vehicles near Coutances. In a standard configuration, he would have made one pass, dropped his bombs, and then been relegated to strafing soft targets with machine guns. On this day, carrying the jury-rigged loadout, he made 4 separate firing passes. He described watching a German tank lift off the ground and settle back down as a smoking ruin after a direct hit from a rocket salvo. When he returned to base, the baling wire holding the empty tubes was scorched, and the duct tape on the landing gear was peeling from the heat of the brakes, but the plane was intact. The crew chief, waiting with a fresh cigar and a grime-streaked grin, simply patted the cowling of the engine as if it were a prize-winning bull. "She held together, Lieutenant," was the only technical debriefing offered. This interplay between the pilot and the mechanic is the emotional core of the story. The pilot gets the glory, the medal, and the newsreel footage. But the mechanic bears the burden of the pilot's life. Every time Sergeant Harrison twisted a wire to secure a rocket tube, he was making a calculation. Will this hold? Will this wire snap under G-load and send a rocket into the propeller arc? The trust required for a pilot to strap into a machine held together with farm supplies is absolute. It speaks to a unique relationship found in wartime aviation, a bond forged in the shared understanding that the manual is a guide, but ingenuity is a lifesaver. The success of these field modifications sent ripples back up the chain of command. Initially, officers from the technical commands were horrified. They saw unauthorized modifications, safety hazards, and a blatant disregard for standard operating procedures. But the photos from the gun cameras didn't lie. The burning hulks of German armor littering the roads of Normandy were the only validation needed. Eventually, the factories caught up. Later versions of the P-47 and subsequent aircraft were designed with zero-length rocket launchers and integrated hardpoints that mimicked the functionality of the field rigs. The improvisation of the summer of 1944 became the standard specification of 1945. However, the legacy of the duct tape and wire Thunderbolt extends far beyond the technical specs of World War II. It represents a fundamental truth about American military history and, perhaps, the nature of warfare itself. Technology is designed in a vacuum, in the clean, well-lit rooms of theory. But war is fought in the dark, in the mud, in the friction of reality. No plan survives contact with the enemy, and no machine is perfect for the conditions it ultimately faces. The gap between the machine as designed and the machine as needed is bridged by the human element, by the adaptability of the 19-year-old sergeant who grew up fixing tractors in Iowa or hot rods in Brooklyn. As we reflect on this narrative, it is tempting to romanticize the Yankee ingenuity and the rugged individualism. And indeed, it is a story of ingenuity. But we must also acknowledge the desperation that drove it. These modifications were not born of boredom or curiosity. They were born of fear and necessity. They were born because men were dying in the hedgerows, and the tools at hand were insufficient to save them. The duct tape and baling wire were not just holding rocket tubes, they were holding the line. Today, if you visit a museum and stand before a restored P-47 Thunderbolt, you will see a pristine machine. The aluminum is polished to a mirror shine. The invasion stripes are painted with geometric precision. The rocket tubes, if present, are mounted with the correct factory-approved hardware. It is a beautiful, sterile object, but to truly see the aircraft, you must imagine it as it was on that July afternoon in 1944. You must imagine the dust coating the wings, the oil stains weeping from the cowling, and the rough, jagged ends of baling wire twisted around the pylons. You must imagine the strips of silver tape peeling in the wind. It is in those imperfections, those unauthorized and unpolished details, that the true history resides. The transformation of the P-47 from a heavy escort into a tank-killing destroyer was not achieved through a breakthrough in a laboratory, but through the stubborn, greasy, dangerous work of men who refused to accept that impossible was a valid reason to fail. They took a 10-minute field fix and altered the course of the war in Europe. They proved that while engineers build weapons, it is the soldiers and the mechanics who forge victories. The echo of those rocket motors, the whoosh that terrified the panzer crews, has long since faded from the French countryside. The hedgerows have grown back, covering the scars of the tank tracks. But the lesson remains. In the calculus of conflict, the most dangerous component of any weapon system is not the explosive, nor the engine, nor the guidance system. It is the human mind, capable of looking at a piece of wire and seeing a way to change the world. It was a Republic P-47 Thunderbolt, known universally to its pilots and crews as the Jug. Standing beside it, a human figure appeared almost comically small. The aircraft was a monolith of aluminum and steel, a 7-ton flying milk bottle that dwarfed the sleek Spitfires and Mustangs operating in the same theatre. Its fuselage was barrel-chested, designed not for the graceful, balletic dogfights of the Battle of Britain, but for the brutal, kinetic physics of high-altitude escort and, increasingly, the dirty work of ground attack. But on this particular afternoon, the massive fighter bomber represented a problem. It was a weapon of immense potential energy that was failing to discharge its power effectively against the one target that mattered most. The logistical chain that supplied the Allied armies was a marvel of the modern world, stretching from the factories of Detroit to the beaches of Normandy. Yet, ironically, it was this massive bureaucracy that created the bottleneck. New equipment, such as specialized rocket launchers, had to be designed, tested, approved, manufactured, and shipped across an ocean infested with U-boats. By the time a new modification reached the front lines, the tactical situation had often shifted. The men in the field didn't have months to wait for the official kit. They had hours. The 9th Air Force, the tactical arm of the U.S. Army Air Forces in Europe, was living in a world of improvisation. They were the rough-and-tumble cousins of the glamorous 8th Air Force. While the 8th flew from paved runways in England and returned to officers' clubs with warm beer, the 9th lived in tents in the dust of France, moving their airfields forward as the infantry advanced. This proximity to the front lines bred a specific kind of culture. The mechanics of the 9th could hear the artillery fire at night. They saw the ambulances rushing back from the front. The war wasn't an abstract concept of strategic tonnage dropped. It was a visceral reality of neighbors killing neighbors. This closeness dissolved the rigid barriers between officers and enlisted men, between pilot and crew chief. When a pilot climbed down from his cockpit, shaking and covered in sweat, describing how he had watched a column of German tanks maul an American infantry platoon because he ran out of ammo, the crew chief took it personally. It wasn't a failure of the pilot, it was a failure of the machine. And if the machine was failing, it was the crew chief's job to fix it. Into this cauldron of necessity and frustration, the P-47 Thunderbolt had arrived as a reluctant savior. Designed by Alexander Kartveli at Republic Aviation, the P-47 was a monster of an aircraft. It was built around the Pratt & Whitney R2000 800 double wasp engine, a piece of engineering so massive it dictated the entire shape of the fuselage. The 18-cylinder, air-cooled radial engine was a marvel of durability, capable of absorbing tremendous battle damage and continuing to run. It was wrapped in a heavy, bathtub-shaped fuselage that protected the pilot and the turbocharger ducting. The plane was fast, diving at speeds that could break the sound barrier's threshold, and it was incredibly tough. But it was heavy. Fully loaded, it weighed more than double a British Spitfire. The Thunderbolt's primary armament consisted of 8 50-caliber Browning M2 machine guns, 4 in each wing. These were devastating weapons against soft targets. A 2-second burst could disintegrate a truck, a locomotive, or a squad of infantry. But against the frontal armor of a Tiger I or the sloped glacis plate of a Panther, the 50-caliber rounds were essentially useless. They would spark and ricochet, leaving the German crews inside, shaken but alive. The pilots carried bombs usually 5 to 100 or 1 to 1,000 pounders, but bombing from a fighter aircraft was an art form that few had mastered. To hit a small, moving target like a tank with a dumb bomb required a shallow dive and a release point that brought the aircraft dangerously close to the ground and the flak. Even then, a miss by 50 feet might only rattle the tank's tracks. The solution, theoretically, was the unguided rocket. The British had pioneered this with the Hawker Typhoon, using the RP-3 rocket to devastating effect in the Falaise pocket. The Americans were catching up with the M8 high-velocity aircraft rocket. The M8 was a 4.5-inch fin-stabilized projectile carrying a high-explosive warhead. It struck with the force of a medium artillery shell. It had no recoil, allowing the aircraft to fire it without losing airspeed or stability. It was, on paper, the perfect tank-busting weapon. However, the delivery system was flawed. The standard American launch mechanism was the M10 rocket launcher. This was a cluster of 3 tubes, made of a peculiar plastic-impregnated paper or sometimes magnesium alloy, designed to be jettisoned after firing to reduce drag. These launchers were aerodynamically dirty, creating turbulence under the wing. More critically, they were in short supply. And even when available, a P-47 was typically limited to carrying just 1 cluster under each wing, giving a total of 6 shots. In the heat of combat, with adrenaline surging and flak bursting around the canopy, a pilot might fire 2 or 3 rockets in a single pass. 6 shots meant perhaps 2 passes. It wasn't enough volume to ensure a kill. This is where the mechanics of the 366th and 405th Fighter Groups stepped in. They looked at the P-47's wing, a structure of incredible strength, and saw wasted potential. The factory specifications said, no more. The center of gravity charts said, unsafe. But the mechanics saw the massive bomb shackles, designed to hold 1,000 pounds of dead weight, and wondered why they couldn't hold a battery of rockets instead. The technical challenge was not just about hanging weight, it was about integration. The M10 tubes were designed to hang from specific mounting lugs. To add more, or to forego the M10 clusters in favor of bare tubes, required a mounting system that didn't exist. So, the ground crews manufactured one. They raided the base dumps. They found steel pipes used for plumbing or construction. They found the shipping crates that the rockets came in. And most famously, they found baling wire. Baling wire is a staple of agriculture, a soft, pliable steel wire used to bind bales of hay. It is not an aerospace material. It has no mil-spec number. It is not tested for shear strength at 300 knots, but it was available. The mechanics began to twist this wire, using pliers to lash additional launch tubes onto the existing hardpoints. They created makeshift clusters, sometimes stacking 4 or 5 tubes together, binding them tight against the sway braces of the bomb racks. But the structural mounting was only half the problem. A rocket is an electrically fired weapon. It requires a voltage impulse to ignite the solid fuel propellant motor. The P-47's cockpit was equipped with a gun trigger and a bomb release button. It did not have a switch panel for a non-standard array of rockets. The electricians, working alongside the mechanics, had to perform surgery on the aircraft's nervous system. They opened the access panels, tracing the 24-volt circuitry. They spliced into the bomb release solenoids, or sometimes the gun camera circuit, creating a new firing loop. This is where the duct tape entered the legend. To get the electrical impulse from the wing root to the jury-rigged tubes out on the pylons, wires had to be run externally. Drills were forbidden on the main spars, so the wires were taped to the leading edges of the landing gear struts or along the bottom of the wing surface. The tape used was not the silver consumer tape of today, but a heavy-duty, cloth-backed industrial adhesive tape used for sealing ammunition boxes or patching canvas. It was strong, sticky, and waterproof. The mechanics taped the wires down, smoothing the edges to minimize drag, praying the adhesive would hold against the slipstream. Consider the engineering audacity of this. The P-47 was a complex machine, its performance calculated to the decimal point. Adding drag to a wing is not a trivial matter. Drag increases with the square of the speed. A bundle of tubes and wires that looks aerodynamic in the hangar becomes a wall of resistance at 350 miles per hour. It creates turbulence that can buffet the tail, causing control issues. It changes the stall characteristics of the wing, making the aircraft more prone to snapping over into a spin at low speeds, exactly the speeds flown during a strafing run. The mechanics were effectively acting as test engineers, aerodynamicists, and manufacturers simultaneously, all while under the threat of enemy air raids and with dirt under their fingernails. They were balancing the desperate need for firepower against the safety of the airframe. They knew the R2800 engine was the key. The double Wasp was a beast. With water injection, it could produce emergency power that exceeded its operational limits for short bursts. The mechanics reasoned that the brute force of the engine could overcome the aerodynamic sin of the modifications. The first tests were informal and terrifying. A pilot, often the squadron commander or a seasoned veteran, would volunteer to take the Frankenstein bird up. They would strap in, the crew chief helping them buckle the harness, a silent exchange of trust passing between them. As the engine coughed to life, spitting blue smoke, the vibration rattled the new, unauthorized appendages under the wings. The takeoff roll was agonizingly long. The extra weight and drag acted like an anchor. The P-47 would eat up the steel planking, the tail wheel lifting sluggishly. Ground crews held their breath, watching the end of the runway approach. When the wheels finally broke contact with the earth, the climb was shallow, but it flew. Once in the air, the pilots found the handling different. The roll rate was slower. The plane felt heavy in the hands. But when they nosed over into a dive and lined up on a practice target, a derelict truck or a marked patch of earth, the payoff was immediate. Instead of the limited swoosh swoosh of a standard cluster, the modified Thunderbolt could unleash a torrent of fire. The ripple fire of 8 or 10 rockets created a saturation effect. It was like a shotgun blast compared to a rifle shot. The pilot didn't need to be sniper accurate, he just had to be close. The operational debut of these modifications in July 1944 marked a turning point in the tactical air war. The target-rich environment of the Normandy breakout, Operation Cobra, provided the perfect testing ground. The German army was attempting to maneuver, to reposition its panzer divisions to contain the American advance. This forced them out of the cover of the deep forests and onto the roads. In the cockpit, the experience was a sensory overload. The pilot would spot the dust cloud of a German column. Rolling the heavy Thunderbolt onto its wing, he would pull the throttle back slightly to stabilize the dive, then push the nose down. The ground would rush up a blur of green fields and grey roads. Through the reflector gun sight, the dark shape of a tank would grow larger. At ranges of less than 1,000 yards, the pilot would press the button. The ignition of the rockets was violent. The propellant motors kicked out a trail of white smoke that instantly obscured the pilot's vision. For a heartbeat, he was flying blind, trusting his trajectory. The aircraft would shudder as the rockets left the rails, the sudden loss of weight causing a momentary pitch change. Then, the smoke would clear, and down below, the earth would erupt. The rockets, traveling at over 1,000 feet per second, slammed into the targets. The shaped charge warheads burned through armor plate. The high-explosive variants shattered wheels and tracks. One specific engagement in late July illustrates the terrifying efficacy of this new capability. A flight of 4 P-47 seconds from the 366th Fighter Group carrying the improvised rocket loads, caught a reinforced column of the Panzer Lehr Division near Saint-Lô. The German commander, hearing the approach of aircraft, ordered his tanks to disperse into the fields. In previous weeks, this might have saved them, but the P-47 seconds now had the ammunition to hunt them individually. The pilots set up a racetrack pattern, orbiting the field and diving in sequence. The first pass disabled the lead and rear vehicles, trapping the column. Then, the systematic destruction began. The pilots didn't just fire and leave, they had enough rockets to make multiple passes. They walked their fire down the line. A Tiger tank, the fearsome predator of the ground war, was helpless against an attack from the vertical. A rocket hit to the engine deck would ignite the fuel. A hit to the turret roof would kill the crew instantly. Within 10 minutes, the road was a graveyard of burning steel. The psychological effect on the surviving German troops was shattering. Interrogated prisoners later spoke of the Jabos with a mixture of hatred and awe, describing how the sky seemed to rain fire. The 86 tanks figure, often cited in the lore of the 9th Air Force, represents a culmination of these efforts over a particularly intense period of operations. It serves as a statistical monument to the lethality of the modified P-47, but behind that number lies a mosaic of individual stories of pilots returning with adrenaline shakes, of mechanics patching holes in wings that had flown too low, and of the constant, frantic work to rearm and relaunch. The turnaround time on the ground was critical. As soon as a Thunderbolt taxied back to its hard stand, the engine ticking and cooling, the ground crew swarmed it. The armourers, shirtless in the heat, hauled the heavy crates of rockets. The wire cutters came out. The duct tape was inspected and replaced. The improvisation had become a standard procedure, a rhythm of labour. The mechanics had refined their technique. They knew exactly how many twists of the wire were needed to secure the tube, exactly where to tape the leads to avoid the landing gear doors. They had turned a desperate experiment into a streamlined process of destruction. We must also consider the human cost of this tactical shift. Flying ground attack in a P-47 was one of the most dangerous jobs in the war. By descending to treetop level, the pilots exposed themselves to everything from light flak to small arms fire. A lucky rifle bullet could sever a hydraulic line or pierce the oil cooler. The jug was tough, but it wasn't invincible. Many pilots who flew these rocket-laden missions did not return. They flew into the ground, target fixated, or were brought down by the sheer volume of ground fire. The extra drag of the rockets made the aircraft harder to pull out of a dive, reducing the margin for error to almost zero. The mechanics who rigged the planes had to live with the knowledge that their modifications, while increasing lethality, also increased the danger to the men they considered brothers. Yet, the momentum of the war demanded it. The breakout from Normandy, leading to the rapid liberation of Paris and the drive to the German border, was fueled by this tactical air power. The P-47 seconds acted as flying artillery for the armoured divisions of General Patton. They cleared the road ahead, smashing anti-tank guns and strongpoints before the Sherman tanks even came into range. The communication between the ground controllers in the tanks and the pilots in the air became a dialogue of combined arms warfare that defined the American way of war. As the summer turned to autumn and the Allied armies moved away from the beachheads, the logistical situation improved. Better, factory-standard rocket launchers began to arrive. The M14 and M15 launchers, and eventually the zero-length stubs that allowed rockets to be hung directly under the wing without tubes, replaced the baling wire and tape. The improvisation faded, replaced by standardized production. The wild, cowboy engineering of the Normandy campaign was tidied up, codified, and made safe. But the legacy of those few weeks in July and August remained. It was a demonstration of a specific operational philosophy, that the people closest to the problem are often the ones best equipped to solve it. The engineers in the United States saw the P-47 as an aerodynamic platform. The mechanics in France saw it as a tool for killing tanks. The friction between these two views generated the heat of innovation. This story also serves as a precursor to the future of close air support. The DNA of the overloaded, rocket-firing P-47 can be traced directly to the design of the A-10 Warthog, decades later a dedicated tank killer built around a massive gun and heavy ordnance load. prioritizing survivability and lethality over speed and grace. The pilots of the A-10 and the mechanics who maintain them share a spiritual lineage with the men of the 9th Air Force. They understand that when the enemy is in the wire, the only thing that matters is how much high explosive you can put on the target and how fast you can do it. Reflecting on the duct tape and wire solution forces us to reconsider our understanding of technological superiority. We often view World War II through the lens of industrial capacity, the number of ships built, the tons of steel produced. We look at the atomic bomb or the proximity fuse as the defining technologies. But there is a micro-history of technology that is equally important. The history of the field modification. It is the history of the hedgerow cutter welded to the front of Sherman tanks, the sandbags on the floor of the Jeep, and the baling wire on the wing of the P-47. These are the technologies of desperation and adaptation. They remind us that war is a chaotic, fluid environment where the rigid plans of peacetime disintegrate. The mechanic who decided to tape a wire to a strut wasn't thinking about the future of aerospace engineering. He was thinking about the pilot who had just told him, "I can't hit them with what I have." He was solving a human problem with the materials at hand. There is a profound ethical weight to this as well. The conversion of the P-47 into a mass destruction machine accelerated the end of the war, undoubtedly saving Allied lives. But it also unleashed a level of violence on the ground that was horrifying to behold. The rocket attacks left nothing but charred metal and unidentifiable remains. It was impersonal, industrial slaughter delivered with makeshift tools. The mechanic, twisting his wire, was an agent of this destruction, a small cog in a vast machine of violence. Yet his individual agency, his creativity, was the pivot point upon which the tactical situation turned. Today, the few surviving P-47 Thunderbolts are prized museum pieces. They sit in climate-controlled hangars, silent and clean. The violence has been scrubbed away. The oil leaks are gone. The smell of cordite and fear is absent. When we look at them, we see the triumph of American design. But if we look closer, if we know where to look, we can see the ghost of the improvisation. We might see the slight discoloration on a hardpoint where a non-standard load was forced. We might imagine the shadow of tape on a strut. These aircraft are monuments not just to the pilots who flew them, but to the crews who kept them flying and the mechanics who reinvented them. They stand as a testament to a moment in time when the rulebook was thrown into the mud and a piece of baling wire became as important as a radar set. They remind us that in the face of existential threat, the human capacity for adaptation is the ultimate weapon. The story of the P-47 Normandy is not just a story of tanks destroyed or battles won. It is a story about the gap between theory and practice, and the men who bridge that gap with whatever they can hold in their hands. It is a story that affirms a simple, brutal truth of warfare. It is not the most sophisticated army that wins, but the one that can learn, adapt, and modify its way out of a corner faster than the enemy can react. The duct tape and wire trick was not a fluke. It was the purest expression of a military culture that valued results over protocol, a culture that took a fighter plane and turned it into a legend, one twisted wire at a time.